right. So we've been talking a lot about primes in this, and one thing that might just be interesting is how many primes are there? So now one thing that is kind of sort of understanding a little bit about sort of just numbers in general, the sort of natural thing might be is just say there's an infinite number, right? So we've talked about, you know, an infinite number of odds and evens type of thing. An infinite number of lots of other things, which is often why we have to do proofs, because we just can't test every single number. So how many primes are there? So there actually are an infinite number, and we're going to prove that here. There are an infinite number of primes. So this little theorem goes back to, I believe, Euclid, so sort of in Greek time, so over 2,000 years ago. But it's a nice little, the other reason for doing this is showing a little different way of proving things. Okay, here's what we're going to do with this. So we're going to, first of all, we're going to assume that there are a finite number of primes. And we're going to call the largest one P. Okay, this is called a proof by contradiction. All right. Typically what you want to do is assume the opposite of what you want to prove. Okay? So we're going to assume the opposite of what we want to prove, and as we're going to see is we want to, there will be a contradiction. Right. So that will result in the original thing being sort of an illogical assumption, and that means that the actual thing that you wanted to prove is actually true. Okay, so this is what we're going to do. So we're going to say that assume there is a finite number of primes, and call the largest one P. So then what we're going to do is we're going to let n equal 2, 3, 5, 7, up to P. And then we're going to add 1 to it. Okay, so we're going to take the product, this is the product of all primes. Right there. And then add 1. Even thinking about this for a small number, it kind of gets a little bit baffling, but you can kind of, you know, throw up into, you know, take the primes under 100, but if you multiply those all together, this already gets really, really large. But here's the idea with this, is that so if I divide by 2, I actually have a remainder of 1, right? Because really what it's sitting there in quotient remainder theorem form, whereas it's 2 times something plus the remainder, right? Well, n divided by 3 has remainder 1 as well. And n divided by 5 has remainder 1. Dot, 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 dot. And then n divided by p has remainder 1. Okay. Okay. So basically what this has shown is that all of the primes, right, if I'm trying to check divisibility by any prime, it's not divisible by any of the primes. Therefore, n is prime. So, what do we conclude? Well, we actually now have a prime that's bigger than p. So let me write the rest of this. Sorry, we're running out of boardroom. N is larger than p, which violates the assumption. I mean, clearly this number is bigger than p, right? Which violates the assumption that p is the largest prime. So there are an infinite number of primes. And proof. Okay. All right. So let me walk through this one more time again. I think it's sometimes see. So again, what we're going to do, and this is a common way to prove lots of other things as well. It's just this, like one of these great little techniques. So I'm going to start with a finite number of primes, and the largest is going to be p, right? So then I'm going to take my number and multiply all of the primes up to p, which is the biggest one, but then add 1 to it. Right? But basically dividing that number by 2, 3, 5, all of the primes up to p always have a remainder of 1. Okay, so basically if any of these came out to be 0, then n would be not prime, it would be composite. But it didn't. Basically this shows that n is prime. Okay, but n now is larger than p, right? Because it's this product of all this stuff, p plus 1. And it's larger than p, which violated the assumption that we started with. Okay, so that p was the largest prime. Therefore, there can't be a largest number p, and so there are an infinite number of primes. Okay, fun little theorem.